Last for today is periodicity and atomic structure. Now, Einstein is famous for his E equals mc squared. And basically, it means all matter has both wavelength and particle characteristics. The greater the mass, the smaller the wavelength, and the smaller the mass, the higher frequency wavelength. Thus, when you get a small particle at a speed approaching the speed of light, then it has what we call dual characteristics, both particulate characteristics and wave-like characteristics. So to say that an electron has a wave property is not entirely facetious at all, but quite true. It does have a lot of wave characteristics. Okay, de Broglie is the one that started this. He said that wavelength is equal to Planck's constant divided by mass times velocity. Now, Planck's constant was derived a long time prior to that, equal to 6.626 times 10 to the minus 34th joules times seconds. Now, Einstein took Planck's constant and did a derivation. We said wavelength is Planck's constant over mass times velocity. Then velocity would be Planck's constant times the speed of light divided by wavelength, or wavelength times velocity equals the speed of light, or E is equal to Planck's constant times velocity. So he substituted everything back in and said that E is equal to Planck's constant times the speed of light divided by what was equivalent to wavelength back here, which is Planck's constant over mass times velocity. And he canceled out the Planck's constants and did a reversal where mv comes to the top of the numerator, and found that E is equal to m times c times v. And if v is close to the speed of light, then you get to say E equals mc squared. And that's the way he derived it. That's how complicated it is. You don't need differential equations, particle calculus, or any of that kind of stuff. It's a simple algebraic function. It's not even algebra, actually. So that was Einstein's special theory of relativity. And I'm not taking anything away from him. The guy was pretty sharp. But he was also notorious for questioning things, which made him a good scientist. Unfortunately, I think you're inundated with a lot of scientists nowadays who tend to follow the herd, not questioning things enough. I find that from a guy who's been in science for 60 years, I find it annoying that there's not more speculation about different theories. Okay, again, you'll have to use your wonderful magnification to get this where it's easily visible. The next one down here is Bohr. And Niels Bohr proves that electrons do not fly off the orbit, because you got things spinning around the speed of light. Why doesn't it fly off? Well, Bohr proves that the attraction for the protons in the nucleus was strong enough to keep the electrons in orbital. That was his claim to fame. And he used the same Planck's de Broglie's derivation previously, and says wavelength is equal to Planck's constant times the speed of light divided by the change in energy. Then Schrodinger came along with his equation, and he said that H is equal to E. And what we call the cactus equation, because it looks like a cactus. And for my humorous attitude towards this, we'll say H cactus is equal to E cactus, E being the total energy of the atom, and cactus being the three-dimensional wave function coordinates of the electron, X, Y, Z. Everything has three-dimensional function. As you're sitting in front of the keyboard, you have a three-dimensional property. Every facet of you has three-dimensional property, X, Y, and Z. And this was an interesting derivation, and it led to a lot of good stuff. This is how they proved electrons also follow patterns. And the patterns are as listed below. Shells is the first column. Suborbitals, the number of suborbitals, is the second column. And the number of orbitals listed is the third column. Now, the first one we've talked about previously has only 2 electrons possible. The first one, the 1s shell, has, in fact, 1 electron, and it defines the element hydrogen. The full 1s shell, with 2 electrons, defines helium. Then we go down the list to the second shell, has 0 and 1 for its suborbitals, and it has the 1s and the 2s plus 2p, x, y, and z. And each of those has 2 electrons in it. As you can see here, 2s, 2p, 2y, and 2z. Next we go to the third one. Third one has 0, 1, and 2 for the suborbitals. It has everything in 1 and everything in 2, plus it has 3s, which, again, all the s shells can never have more than 2 electrons. It has 3p, and none of the p shells can have more than 6 electrons. And it has 3d, which you can see there, 2, 4, 6, 8, 10. It can never have more than 10 electrons. So if you added up all the electrons in the third shell, there would be 10 plus the second shell, which has 2, 4, 6, 8, so it's 18, plus the first shell would be 20. So that would be the number of atoms that you can easily describe their suborbitals and the orbitals of the electrons. Okay, we'll go back to the pattern. The pattern of these is called the quantum numbers. Pauli's principle was in the same atom, no 2 electrons can have the same quantum numbers. In other words, no 2 particles, and this has been extended to quantum physics, no 2 particles can occupy the same space at the same time. Now, you can rightfully say, duh, because that's logical. As much of this stuff, it sounds kind of complicated in a way. If you had to do the mathematical derivations, it is pretty darn complicated. But reality is, it is not that complicated to understand if you try to reach for it, relatively speaking. You can understand that if you're sitting in a chair, no other person or no other being can occupy that chair at the same time. And that's all that really says in Pauli's principle. Now, Aufbau said for stable atoms, the protons in the nucleus equal the number of electrons in orbit, which I told you from day one when we started talking about Mendeleev's periodic table, that there's always a proton in the nucleus for every electron that's orbiting. But he had to put it as a rule. So that's Aufbau. They call it Aufbau's principle. Next, we have Hund's rule for the orbitals. And the orbitals are basically because of electrons' repulsivity for each other. Remember, they don't like each other. They want to stay as far away as possible. Thus, when they're in the suborbitals, they revolve opposite to stay as far away as they can. So Hund's rule says for every type of atom, for every orbital, it is due to the repulsivity of the electrons, and this is the most important factor in the whole doggone thing. The outer electrons are called valence electrons. Write that down. The outer electrons are called valence electrons. Now, get your ability to draw this in and make it a full page, and it's easy to write down, and it's easy to follow. Make sure you got your book, because all the books have some of this in it. Not all of them have all of it, but virtually all the books have some of this in it. And hopefully that helps your explanation.